Good morning, Ben Cohn. Time for calculus review. So I've already covered pretty much all the rules that we're going to do for derivatives. Now we're going to kind of review where we've been and kind of what you need to keep in your mind. So our first endeavor was limits. So the idea was we have some sort of indeterminables. What if we have an infinite amount of nothing, so to speak? Do we have a lot? Do we have a little? We don't know. And the indeterminates kind of come in forms of 0 over 0, infinity over infinity, or 0 times infinity, or infinity times 0. And there's more, but these are the ones we kind of focus on. And the way we decided to attack these was through limits. And so one of the things we'd see would be something like limit as x approaches 0 of, let's say, 6x cubed plus 2x squared plus 9 over 3x cubed plus 2. And we're like, okay, as x goes to 0, let's throw in some x's here. There we go. As x goes to 0, what is the value here? Well, we have all zeros on top, we have all zeros on bottom, so we really don't know. And one of the key points to know about limits is from a graphical point of view. You have a function that looks like so, and you're trying to find the limit of some point, let's say right here, point C. Then the function doesn't actually have to exist at that point. F of C doesn't have to exist. It just has to be the same from the left side and the right side. So the limit as x approaches C, if you have limit as x approaches C from the left side, which is represented by the negative, and that's the same as your limit as x approaches from the right side, basically from the left side from the right side, then that will equal, they have to equal each other. Then you have the limit as x approaches C in general. That's the idea from left side equals the right side, and that equals the limit. But this point right here, even though I drew it as a solid dot, it doesn't actually have to be a solid dot. You can have an open dot, meaning that that point doesn't exist. So if it's getting close to it on the left, getting close to it on the right, that's good enough. So if you zoom in, it looks something kind of like this. Something here, really close, exists. Something right there, really close, exists. The center doesn't actually have to exist. That's the idea of a limit. This also came into the idea of continuity. If a function is continuous, then it means you can draw it without picking up your pen. That's not the formal definition, but it's pretty much darn good. And for anything that you would reasonably do, not picking up your pen is a good enough definition for continuity, especially for the AP exam. So the way we would approach this then is we learn to approach this by factoring out the x's. Well, let's call this one an x cubed. So then we would say that, all right, limit as x approaches 0 of x cubed over x cubed, and then we'd have something like this. Let's say as it goes to infinity. I know I keep changing the problem. Bad form, plus 2 over x plus 9 over x squared, because we factored out the x cubed, 3 plus 2 over x squared. And what we got going on here, what happened here, was this would then go to 0, because we were going to infinity. This would then go to 0, and the x cubed would cancel out, and then we'd be left with 2. And we did that for a handful of them, but we kind of reached a limit of what was possible. And for that, this is kind of jumping over derivatives, but we used L'Hopital's rule, which is what the vast majority of limits they'll be asked to analyze or questions about on AP exams will deal with L'Hopital's rule. So L'Hopital's rule, to backtrack, was limit as x approaches C, some constant, of f of x, g of x, where that gives you an indeterminate form, infinity or infinity, 0 over 0, or some such. would equal the limit as x approaches c of f prime of x over g prime of x. This is presented without any justification or proof. So one example, this could be 2 times natural log of x all over x minus 1 as the limit as x approaches 1. And so we try and plug in 1 to kind of see what happens. And we get 2 times natural log of 1 all over 1 minus 1, which is 0 over 0. And this gives us an indeterminate form. 2 times natural log of 0 all over 1 minus 1. Natural log of 1. Natural log of 1 equals 0. And so this gives us in 0 over 0, which we can't really do anything with it because it's indeterminate form. But this gives us an opportunity to use L'Hopital's rule. So we take the derivative of the top, take the derivative of the bottom, limit as x approaches 1. The derivative of natural log of x is 1 over x. And derivative of x is 1. So then when we plug in 1 here, we have 2 over 1 over 1, which then just gives us 2. One of the things you might be tempted to do at this point, or previous during this process, is you're like, okay, we have an f of x over g of x. We're going to do the quotient rule, but then I like to do the quotient rule like through the product rule. And you start thinking of how to take the derivative of this function as a whole. That's not what you do here. You take the derivative of the top, you take the derivative of the bottom, and that's it. Then you put them right on top of each other. You don't try and do anything product rule. This isn't a derivative of the whole thing. This is L'Hopital's rule, which operates differently. So don't let that trip you up. Okay, so that was how we dealt with limits. Now, backtracking slightly, back to derivatives. When we talked about derivatives, we talked about how derivatives were, in concept, dy dx, rise over run. And we had dx here, we had dy here. We said derivative would be dy dx. And I used delta to show that it's a small finite amount. Usually when you convert this over to dy dx, which is the more formal derivative, that this d basically represents an infinitesimal amount. So finite, infinitesimal, small. And so our definition of the derivative was, this is x. We call this x plus h, where h is going to approach 0. This would be f of x, or I guess y of x. And this would be f of x plus h. So using the idea here, we had the definition of a derivative, f prime of x, where prime is the same thing as saying the derivative. And it's just implied that the derivative is with respect to x, not explicitly stated. So we could also say derivative of x, f of x, like so. Same thing, just different notation, which is pretty much the same as well as dy dx. So what we did for the definition of the derivative was we just did rise over run, f of x plus h all over, and then I write x plus h minus x. And I do it that way because then it's more obviously rise over run. A lot of people will just cancel out the x's and just leave an h on the bottom. And then you take the limit as h approaches 0. And one of the thought processes when you see this is, well, it seems kind of lopsided. We're trying to find the derivative at that point there, but we're only using the right side here. Shouldn't we use the left side as well to kind of, balance out the whole system here? And that's true. We're doing a less good approximation here by just taking the right side, x and x plus h, instead of using x plus h and maybe x minus h per se. You're right, but the thing is, since we take h approaches 0, that means that even if we have a mediocre approximation, a method of taking the approximation, as h goes to 0, it becomes infinitely good. And if we have an infinitely good mediocre approximation, it's still perfect because that h going to 0 refines it to the umpteenth perfect level, basically. That was a terrible explanation, but I'm going to go with it. Stick with it. Play it through. But what that also means then is if you want to, for convenience based at some point later in life, and I think I use this with finding the derivative of sine of x, you can use f of x plus h and f of x minus h. And so there's no reason you can't do that. And if you wanted to instead use f of x minus f of x minus h, you could absolutely do that as well. Then you'd have to change the bottom to x minus h, and you use minus h. Not a big deal. I guess it still would be plus h. Not important. So the idea here is you could kind of fiddle around with the definition of the derivative. And it's better to understand it than to just have it memorized through rote memorization. That's the definition of a derivative. And we use that to basically come up with a whole bunch of rules which make our life easier. Because if every time you come across a function, you're like, okay, I'm going to take this magic definition of derivative and apply it to this function, it'd take you a long time. It's not efficient. So then we came across our first rule that we talked about was the power rule. So if we have the derivative with respect to x of x to the n, that would then go to nx to the n minus 1. And we just, when we proved that, we plugged it into the definition of a derivative, did some algebra, and eventually figured out, okay, this seems reasonable. I think we ended up using a binomial expansion and Pascal's triangle for that one. So a little bit of a interesting endeavor, a fantastic trek, if you will. Then we looked at the product rule. So the product rule is you have u, v, which are two functions. This is the same as f of x times g of x. And more clearly, in this case, this is u of x, u, times v of x. These are functions of x. This is all the same thing that I'm written here. I just write u and v because it's convenient. I usually write out the product rule every time I use it, just to keep things straight and clear. So I like to use u and v. And if you have u and v are both functions of x, and you take the derivative with respect to x of this uv quantity, you'll find uv prime plus u prime v. And usually when I do the product rule, I write it out like I write out this is my first line, and I do u equals whatever u equals, v equals whatever v equals, and then you have to find u prime and v prime. And then you put it all together and you get your answer. One caveat that came out of this was the quotient rule. Quotient rule. So the quotient rule is basically, instead of saying the, so we have, it's as if you had f of x over g of x. Well, what I would usually say then in this case is this is not f of x divided by g of x. This is f of x times g of x, where g of x goes to the negative 1 power. That's kind of the chain rule, which we'll talk about in a sec. So then what you get then is you get a uv to the negative 1. And then you take the derivative of such. Derivative sign and derivative sign. So the idea here then is, there is a quotient rule. You can derive the quotient rule if you want by just plugging this into your product rule and churning through the numbers. But I don't do that. It's just one more thing for me to forget. I have the memory of a goldfish, and there's only so much space, real estate on the iceberg for my penguins. So I don't memorize the quotient rule. I just do the product rule and then rewrite the quotient in terms of a product rule. For me, it works better. That then brings us to the chain rule. So the chain rule, blue, was the idea of taking the derivative of nested functions. This one is a little bit less intuitive than some of the others, but you'll come across it all the time, and you kind of have a sense for the feel of it. Whereas the product rule, I write it out every time. I usually don't do that for the chain rule. And that's just because it's usually pretty easy to keep everything track when you're doing the chain rule, but it saves you a lot of time by not writing it out. There are times when you get a confusing enough problem that it's worth it, but as a general rule, I don't. So the idea with the chain rule is you have your f of x, which is this exterior function, and nested inside this f of x is g of x. So when you take the derivative of g of x nested within inside f of x, what you do is you take the derivative of the exterior, multiply it by the same interior, g of x, and multiply it by the derivative of the interior. It kind of makes sense when you see it. It has a good feel to it. So you have sine of 3x derivative, and so this would be then the derivative of sine of x, which is cosine of x, maintain the sign, and then you keep the same 3 of x, and you multiply it by the derivative of 3x, which is 3. So here, sine of x, sine goes to cosine, the 3 of x stays put, but then you have this, little jump, goes to the g prime of x over there. Looking at it similarly up here, g prime of x, g of x, f prime of x. And it does take a little bit of practice to kind of get that fluid going. And you can do it multiple times as well. So if you had something like sine of 3x quantity cubed, then you'd have to do multiple chain rules, or squared. You would have to do multiple chain rules, which is fine. You can absolutely do that. Not a problem. And then again, that's how I convert the product rule, the quotient rule into a product rule. So if you have uv to the negative 1, this is a nested function here with v taken to the negative 1 power, so use the power rule. Next, we talked about constants. Now, it feels kind of weird that we talk about constants. I think it'd be one of the more simpler things, so we do that at the beginning. Constants, if you have a constant, something along the lines of f of x equals 2, then it makes sense that the slope, dy dx, would be 0. So if f of x equals 2, f prime of x would equal 0. One of the interesting caveats, which simplifies life greatly, is you have something like 3x squared, a constant times something that's a function of x. Then you can take the 3, basically you factor the 3 out, and multiply, then take the derivative of the x squared, which is 2x, and you're left with 6x. Now, you really can't do that the way I said. You can't really just factor out the constant. What you're actually doing here is the product rule. But one part of the product rule equals uv prime plus u prime v, where I said u equals 3, v equals x squared, v prime equals 2x, and u prime equals 0. Well, the u prime equals 0 times v is just 0. So all you're left with is 3 times 2x, which is what we put up here, which is 6x. So it's easier and quicker and more efficient and less prone to human performance traps when you just view the visually mnemonic-wise, take the constant, feel like you're factoring it out, taking the derivative, and then putting it back in. So that's the idea with constants. So then after constants, we look at e to the x. So the derivative with respect to x of e to the x just stays e to the x. So some of the interesting things that come from that is you still have to, consider the product rule, or the chain rule. So if you had e to the 2x, where 2x would be the interior, the nested function, the g of x and your f of g of x, if you will, then you'd have e to the 2x times derivative of the interior, which would be derivative of 2x, which would be 2. So you'd have 2e to the 2x. One interesting caveat that comes to this is when you see something that's not e to the x. So derivative of 2 to the x. You'll see this a handful of times, maybe one, maybe two problems on the AP exam where they ask you about this. So it's not common and it's not worth memorizing, but it's good to know the kind of flow that happens when you're trying to do this. So the first thing you do with this is you take e to the 2x, and you rewrite it as e to the natural log of 2x. 2 to the x. There we go. Which we can then rewrite as e to the x times natural log of 2. This is just your basic log rules. And then we can take the derivative of this, derivative with respect to x, of e to the x, natural log of 2. Natural log of 2 is now just a constant, so we treat it as a constant. And we have e to the x times natural log of 2 times the derivative of the interior function, which is this up here. Derivative of x times natural log of 2 will just be natural log of 2. So then we have, from there, we rearrange it again, put natural log of 2 over on this side, and then we have e to the natural log of 2 to the x again, basically put it back, and that gives us natural log of 2 times 2 to the x. And your thought process might be like, wow, how's, e is just a number, but why is it that when we do something with e not as the base, why does it come out as different? Well, you get a basic formula that you could write out, that whenever you take the derivative of, I'm going to say, some constant a to the x, that's going to be the natural log of a times a to the x. Well, if a in this case was e, then what you come up with would be natural log of e times e to the x, and natural log of e just goes to 1. So really, when you're trying to find the derivative of e to the x, you're really going through this whole process every time. You just don't realize it because you get natural log of e at the time every time. That's 1, and you're just multiplying by 1. So you'll see this maybe a couple times. It's worth knowing it exists, and it's worth knowing how to go through this process. I wouldn't bother memorizing this derivative formula. It'd be good to kind of be able to recognize it, and so when you mess up trying to do this process, you're like, oh, doesn't feel right, I probably messed up. And then going on after derivative of e to the x, we have the derivative of natural log of x. So we have derivative with respect to x of natural log of x is 1 over x. And one of the peculiarities or unique attributes of derivative of natural log of x is the derivative of a constant here will still give you the same answer. Natural log of 1 over x. And you'd expect there to be a 3 involved, and there is a 3 involved. The problem is there's a 3 involved here, and then there's a 3 involved up here. They cancel out, and they give you 1 over x. That's due to the chain rule. So when you see that, don't be too surprised. We also spoke about the parametric and polar equations. So when you have polar equations, you'll get something r of theta equals some sort of function of theta. You might be asked to find the slope at some given point of this curve. And the way that I recommend thinking about it is, instead of memorizing the formula, which there's a formula and it exists, think of it as dy d theta. So slope is always dy dx, and dyx is dy d theta over dx d theta, because when you are dividing fractions, you're multiplying by the reciprocal of the bottom or the denominator. So you get dy d theta times d theta dx. The reciprocal means you basically just flip it upside down, and you get left with dy dx. Now this isn't formal. This is more mnemonic than being formal, but I still like it, and it still works great. So this is how I remember which formula to use when you're looking for the slope in polar curves. And the other key point that you need to know is y equals r sine theta, x equals r cosine theta, and both of these come from a right triangle of x, y, r, and theta. So then we also talked about, this led us into parametric equations. Now parametric equations is you have some sort of x of t, mostly, and you have some sort of y of t. You could have z of t, but mostly probably y of t. And you have some function here, have some function here, and you're trying to find dy dx. Well, the easiest way to normally do that then would be the same as above, where you do dy dt divided by dx dt. You find x prime of t, scroll down, you find your y prime of t, and then you put them in, divide the two, and you get some sort of slope, or derivative, which will then give you the slope at any given point. And there could be some nuance in that, but you work through it, and there's might be small tricks, but nothing that you can't overcome. Polar and parametric problems are rare enough that I don't recommend memorizing formulas for them, just kind of understand what's going on. But part of being rare and unique is that you're going to panic when you see that. You're like, polar, don't know what to do, and that's okay. Panicking is just fine in life. Spend a couple, seconds panicking, but after that, you only got 2 to 3 minutes for multiple choice questions, a few minutes for free response. You usually get about 15 minutes or so for a full free response question, but if you have 5 parts, then you really only get about 3 minutes per part, which is not a lot. So, panic, but do it quickly and expeditiously and move on with life. And hopefully this will give you an idea of where to start your adventure, where to go towards, so that your panic can quickly pass and you can resume your journey. Now, the only other thing we talked about, for the most part, was linear approximations. It felt kind of like an outlier, but it shouldn't. So the idea with linear approximations is you have some sort of graph that you're trying to approximate new points on, and you're given some sort of x here, we'll call it x initial, and you have some sort of x final here, and you have so many steps you want to take between one and the other, and you take the derivative, multiply by a step, and you work your way up to an approximation point. And the way we do this is we set up a table. So this is like Euler's approximation, linear approximations. And you start with x, y. This will be your initial point, your initial x, your initial y. You have a dy dx, because you're usually given some sort of derivative to work with. And then you'll find the change of x, which will be your step. And you'll have a change in y, which will be your dy dx times your delta x times your step. This is what makes it a linear approximation. Then you have your change in y. And then your x1 will be your x initial plus delta x. Your y1 will be your y initial plus your delta y, which you calculate right here. And then you continue on for however many steps you have. Usually you'll only be given 1 or 2 steps. Probably 2 steps, because the AP exam will want to see that you understand how to do multiple steps, but they don't want to have so many steps that you get bogged down in just the computational part of it. Euler's approximations tend to take a while, because you can see, we made a whole table here with 5 columns, and if you have more than 2 or 3 rows, it's going to take a while. And so what you're going to see on the AP exam is usually maybe 2 or 3 steps. And you do this a few times, you get an answer, and you give it back. And for this, I really recommend understanding what's going on as opposed to trying to memorize things. The only thing I'd memorize would be this top row here for your table. And you use that table, you fill it out, and if you do like 3 or 4 of these problems, then you'll pretty much understand how to do it forever. It's not that challenging. It's not that conceptually challenging once you finally get it down. It feels pretty solid. It's a good foundation. It's a very solid igloo once built. And that's the idea behind linear approximations, or Euler approximations as they're called. One other thing that we talked about was graphing, which is kind of similar to this, but it was the idea of sine charts. So when you're given a mystery graph, one of the things I like to do are sine charts. This helps you find maximum and minimums. So you have, what I usually do is I write f of x, f prime of x, and then depending on if they're asking for what they're asking for, maximum, minimums, or even concavity, I'll do f prime of x. And it's easy to write these out. What you do then is you find the roots. So the roots will be where the function crosses the x-axis, where y equals 0, and then I write the roots right here. Then you find the derivative and set it equal to 0, which gives you critical points. So critical points would then give you, is where f prime of x equals 0. And then you can then use this to find slope going up or slope going down. And this will help give you a maximum or minimum. So you'll be like, oh, this is probably a minimum here. And this would be minimum based on the first derivative test. You'll be like, okay, so it comes down, then starts going up, reaches a minimum at a critical point. This is going to be a minimum. So then you'd have a minimum at this value of x. You can also find the second derivative and find the concavity of it. So concavity I then draw as like a smiley face or a frowny face. So in this case then I could tell that it'd be a smiley face, concavity up, and one way you can think of concavity is holds water or doesn't hold water. So this is a positive concavity because if you water rained down on it, this would then fill up with water. This is a negative concavity because if water rains down on it, it would just slide off the edge. You can use this to tell it's a minimum too, because you look at this frowny face like, oh, or smiley face, look at this smiley face, and you can see that, okay, that's a minimum there based on the concavity. And so even though you can't use, this is called a sine chart, you can't use a sine chart to be like, okay, here's the sine chart that justifies that it's a minimum. The correct way to use this would be using the sine chart, or based on the second derivative test, second derivative, this point right here is a minimum. Or if you didn't have access to the second derivative, or you just didn't want to go that far, you just want to use first derivative, you have arrows going down, arrows going up, or which represents slope going down, slope going up. Based on the first derivative test, this point right here is a minimum. And so that's how you use sine charts to determine how a graph looks, graph characteristics, and more importantly for identifying maximum and minimums, which you'll get plenty of maximum and minimum questions. And that covers basically everything we need to know about derivatives for Calculus BC exam. So I know it feels like a lot, and it is quite a bit, but it's nothing superhuman. And once you get you got basically the fundamentals down at this point. From here, you basically just have to do lots and lots of practice. Do some practice, get really comfortable with it, and then you'll be set. So at this point, you should have all the information you need for the second part of this, where it will go over integrals. One of the nice things about, people ask which is harder, the first semester of calculus or the second, the derivatives or the integrals. And it's basically whichever one you don't know the best. If you do a good job of learning derivatives, then you spend a lot of effort learning derivatives, and then integrals are easier. If you do kind of a mediocre job learning derivatives, then the second semester is more difficult because you really didn't get the good foundation. And so I recommend, putting your work up front and trying to learn derivatives as best you can. So thank you much. I'll see you guys on the next class where we start talking about integrals, antiderivatives, Riemann sums, and area under the curve. Thank you much. See you next time.